Okay, lesson number 1 looks at logical reasoning and set theory. So it's the study of collections of objects. So we're going to work with Venn diagrams, we're going to work with set theory, we're going to learn a lot of terminology in this unit, so you will have to keep focused on that. So in this lesson, what we're going to look at is we're going to look at specifically the words and, or, and then the word not in terms of what it means mathematically. So in math, we deal with statements all the time. A statement is a sentence that has a truth value, meaning it could be either true or false. That's what a truth value means. A sentence that is true by one person and false by another, that's not a statement, that's an opinion. So if you consider the following, the city of Vancouver is in the province of British Columbia. It's a statement, it's true, and it's a fact. The city of Vancouver is on the planet of Mars. This is false, which makes it a statement, because it's either true or false. Vancouver is the best place in the world to live. It's not a statement, because depending on who you ask, some people will say yes it is, and some people will say no it's not. And then how do you get to Vancouver? That's no longer a statement, that's a question. So what we're going to do with each of the following is we're going to determine whether or not it's a statement. And if it is a statement, list its truth value, meaning is it true or is it false. So if you want, try to do this on your own, and then when you're ready, you can press play and see whether or not it matches up. So the number 4 is a prime number. Prime numbers are numbers that only have 2 multiples, itself and 1. And 4 has 2. 2 and 2, and then 4 and 1. So it's not a prime number, which means it's false, but it also means that it's a statement because it's a truth value. Driving in a car is the best mode of transportation. This is not a statement, this is an opinion. Okay? There are plenty of people that would say driving is the best mode of transportation. There are plenty of other people that would be like, nope, let me fly any day of the week. If you double an odd integer, then you get an even integer. So this is a statement, but now we have to determine its truth value. So even if you just grab some odd numbers, odd integers, 3 plus 3, I get 6. 5 plus 5, I get 10. If I get bigger, if I go 67 plus 67, I'm going to get 134. At this point in time, it looks like this is a true statement. If you remember from last year when we did proofs, you can prove this. An odd integer, we declared last year that an integer, an even integer, is taking any number and doubling it. Any number and I double it is going to give me an even value. If I add 1, I'm going to get an odd. So if I double this, so if I multiply this by 2, I get 4n plus 2 with the distributive law and multiply this through. This is a multiple of 2, so it has to be even. So that would be the proof of it for every single occasion. So now we're going to look at the word not. So it's the negation of a statement. So the negation of a statement is the exact opposite. The word not is often used to form the negation. For instance, one way to write the negation of the statement, the city of Vancouver is in the province of Alberta, is to say the city of Vancouver is not in the province of Alberta. If the original statement is false, the negation would be true. And if the negation is false, then the statement had to be true. They both can't be false and they both can't be true. Okay? It would not be correct to say that the negation of the above statement is the city of Vancouver is in the province of Saskatchewan, because both this statement and the original are false. The negation always has to be the opposite of the truth value of the original statement. So if we look at class example number 2, a student made the following statement: all triangles are isosceles. Which of the statements below is the negation to that? So we know that triangles can be scaling, they can be equilateral. So we know that that's a false statement. So if I look at this first one, all triangles are not isosceles. This means that none of them are isosceles. So that's not true. And if this is false, this statement here has to be true. If I look at C, all triangles are scaling or equilateral. Well, that's a false statement because some of them can be isosceles. So that's not true. So not all triangles are isosceles. This is a true statement. Not all of them are. Some of them are, but not all of them. That's my negated statement. So again, if you want, try to figure out what the negated statements are for class example number 3 before we do them on the board. Okay, so if the statement is it's 20 degrees Celsius outside, the negation would be it is not 20 degrees Celsius outside. If the statement is it is not Saturday today, then the negation of that would be it is Saturday today. It would not be correct to say that it is Friday or it is Monday or anything else. It is Saturday. Okay, so now we have compound statements. Just like in English class, a compound statement we get by forming 2 or more other statements using the words and or. So for example, it is 20 degrees outside and it is not Saturday today. Or the other statement, it is 20 degrees outside or it is not Saturday today. These are considered to be compound statements. So the conjunction of 2 statements can be formed by using the word and. A conjunction is true only if both of the original statements are true. If otherwise, it's false. So the conjunction of blue is a color with ice is a solid is the statement blue is a color and ice is a solid. This is true because both statements were true. Original statements were true. If I have wet as a color with ice is a solid to give me this statement, wet is a color and ice is a solid, it is false because one of the statements was false. The conjunction of wet is a color with ice is a liquid gives me wet is a color and ice is a liquid. This is false because at least one of the original statements was false. In fact, both of these statements are false. So then we have the compound word or. In everyday English, we can use the word or in different ways. And there is a very big difference between how we use the word or in everyday English. So in order for Drew to have the necessary prerequisites to go to college next term, he needs to pass grade 12 physics or pass grade 12 chemistry this semester. What this statement means, sorry, the camera's flickering, I'm trying to fix it. This means that he can pass grade 12 physics alone, or he could pass grade 12 chemistry alone, or he could pass both of them. So this is what we consider to be inclusive use of the word or, meaning that it could be one or the other, or it could be both. John asks Helen how she's getting to school tomorrow, and she replies, I will take the bus or drive myself. This is exclusive. She cannot do both. She can't take the bus and drive. She does one or the other, and we're not going to get into the, oh, well, she could drive to a park and ride and then take the bus. She's doing one or the other. So when we use the word or in math, the word or in math for us is always going to be inclusive, meaning it could be one or the other or both. So the disjunction of 2 statements is formed by placing the word or between them. So a disjunction is only false if both statements are false. It is true if the first statement is true, or the second statement is true, or both statements are true. Okay, so let's look at the last example. Ivan rolled a pair of dice, and the sum of the two numbers was an odd number or a prime number. So it means that the sum was either an odd number, or it was a prime number, or it was both an odd and a prime number. So if I think about if I roll a pair of dice, I have 1 through 6 in one dice, and then I have 1 through 6 in the other. So if I just created a chart, just to show you how I can answer this question. 1, 2, 3, 4, 5, 6. And then if I fill the chart in with the sums, so I have 2, 3, 4, 5, 6, 7, because 1 plus 1, 1 plus 2. Then I'm going to have 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. We start to see some patterns. 7, 8, 9, 10, 11, 12. So if I roll 2 dice and I get a 2, this is a prime number. A 3 is a prime number. 5s are a prime number. 7 are prime numbers. And that's it. Those are my prime numbers. But if I look at odd numbers, I can also add 9. Oh, sorry, I forgot. 11 is a prime number. So what I have is I have that 3, 5, 7, and 11 are odd numbers and prime numbers. So they would be in my set. 9 would be in my set because it's an odd number. And 2 would be in my set because it's a prime number. So if I was looking at the set of numbers that was odd and prime, those would be that entire set. It would be 2, 3, 5, 7, 9, and 11. So 2 would be my prime number, 9 would be my odd number, and then these ones would be both prime and odd. And it's something to pay attention to because when we start looking at Venn diagrams, this is going to help us draw those diagrams. Okay, so let's look at class example number 4. Consider the natural numbers that are less than or equal to 15. So natural numbers, if you remember from Math 10, natural numbers start at 1. There are counting numbers. If we went and asked the kindergartners, that's what they would start at, is they would go 1, 2, 3, and we're going to count all the way up to 15. So there are my 15 numbers. So the question is, list the set of numbers that satisfy each possible condition. So the first condition is that the number x is odd. So if I list off all of my odd numbers, 1, 3, 5, 7, 9, 11, 13, and 15. So if you want, now that we have those list of numbers up, if you want to pause and go through these 7 examples, and then when you're ready, you can start playing again and you can see what the answers will be. Okay, so if we look at the next one, where x is a prime number, prime numbers again have 2 factors, itself and 1. 1 is not a prime number because it only has 1 factor. So my prime numbers are 2, 3, 4 is a factor of 2, so it doesn't work. 5 works. 6 does not because it has 2 and 3. 7 works. All of the even numbers no longer work because they have a multiple of 2. 9 doesn't work because it has a multiple of 3. I skip to 11, skip to 13, and 15 doesn't work because I can divide it by 3. So those are my prime numbers. So then C says, what are the numbers that are odd and prime? So these were my prime numbers, these are my odd numbers. Look for the overlap. 3 is an overlap. 5 is an overlap. 7 is an overlap. 11 is an overlap. And 13 is an overlap. So those are numbers that are both odd and prime. So then D is a bit different. D has the word or. So remember, the word or means it could be odd, or it could be prime, or it could be both. So if I look through this list, it's basically taking this list and combining it with this list. So 1 is odd, 2 is prime, 3 is both, 5, 7 is both, 9 is odd, 11 and 13 is both, and 15 is odd. So it's either odd or prime or both. Question E, X is a factor of 3, 5, or 7. So if I look at my factors of 3, I've got 3, 6, 9, 12, 15. If I look at my factors of 5, I've got 5, 10, and 15. And my factors, the numbers that are factors of 7 would be 7 and 14. So I'm looking at skip counting multiples. So 3 works, 5 works, 6, because 6 is a factor, 3 is a factor of 6. Or sorry, I read that wrong. Let me start over. The number has to be a factor of 3 or 5 or 7. So if I made factor trees, the factors of 3 are 1 and 3. The factors of 5 are 1 and 5. The factors of 7 are 1 and 7. So it has to be a factor of 3 or 5 or 7, meaning it can be a factor of 3, just 3, it can be a factor of just 5, it can be a factor of just 7, or it can be a factor of all 3. So that would be 1, 3, 5, and 7. F reads a little bit differently because in F it has to be a factor of 3 and 5 and 7. So the only one that is a factor of all 3 of them is 1. Okay. Now G is the multiples. That's where I was getting confused. So G looks at the multiples of 3, or the multiples of 5, or the multiples of 7. Meaning it can be a multiple of 3, but not necessarily a multiple of 5, or not necessarily a multiple of 7. So multiples of 3 are 3, 6, 9, 12, 15. Multiples of 5 become 5, 10, and 15. And then we have our multiples of 7, which would be 7 and 14. So that would be my list of numbers: 3, 5, 6, 7, 9, 10, 12, 14, and 15. If it would be easier, you could list them in 3 different rows and then combine it to put it in numerical order is how you would present it. And then in H, we have that word and again. So it has to be a multiple of 3 and 5 and 7. Well, 15 is a multiple of 3 and 5, but it's not a multiple of 7. In fact, in this list, there is no common multiple. So we would say that there's none in my set from 1 to 15. There is a number, or there could be a number that is divisible by all of them. We just haven't found it yet. Okay? So what I would like you to do for practice questions is numbers 1 to